Welcome to AI Paperslop. For the AI researchers and ML engineers joining us today, what if I told you that the larger a neural network gets, like the more physical parameters you actually add, the less space it takes to perfectly describe what it learned?
Yeah, it sounds completely backward, but it's real.
It is. And today we are jumping straight into the paper that mathematically proves it. It's called Requential Coding, Pushing the Limits of Model Compression with Self-Generated Training Data by Shikai Q, Mark Finzi, Yujia Zhang, Kun Zhang, and Andrew Gordon Wilson.
This paper is, it really fundamentally rewrites how we measure model complexity.
Right, because to give you the core insight right off the bat, current model compression techniques like post-training quantization, PTQ, they're fundamentally bottlenecked.
Exactly. They scale with the parameter count, and then on the flip side, you have prequential coding, which compresses based on data, but that scales linearly with the data set size and, raw data entropy.
Which is massive. So this paper introduces a third path, Requential Coding. It compresses models by encoding the training trajectory using self-generated candidate data.
Right, and it's guided by a teacher model. Because the code only records when the teacher and the student disagree, the length of that code is entirely independent of model size and data entropy.
It's amazing. The math literally proves larger models are more compressible per parameter.
Yeah, and it yields state-of-the-art PAC-Bayes generalization bounds for billion-parameter compute-optimal LLMs. Plus, it perfectly isolates the true learnable structure of a dataset from just random noise.
So before we get into the actual mechanics of this self-generated data stuff, I think we should establish why this bottleneck in measuring compression is such a massive problem for the field right now.
Well, in machine learning, compression is essentially the ultimate empirical test of Occam's razor.
Right.
If you can take a massive data set and compress its underlying rules into a smaller model, that model hasn't just memorized the data, right? It's learned actual generalizable features.
But finding that true compression limit for billion parameter models has just been a brick wall.
It really has. The field has essentially been trapped between two highly flawed paradigms. The most common one you see in engineering is parameter-based compression.
Like PTQ.
Exactly. If you look at post-training quantization, even in idealized, mathematically perfect 4-bit PTQ, it forces your code length to scale linearly with the physical architecture.
Which makes a pretty fatal assumption, right? That the bit width of a parameter equates to its actual information content.
Yes, and that falls apart immediately in edge cases.
Oh, totally. Like if I initialize a billion parameter model and train it on a toy data set of, say, 5 images, the actual information that model has absorbed is mathematically tiny.
Right, it barely learned anything.
But PTQ will still spit out this massive file size because it's measuring the container, not the contents. It's like trying to evaluate the size of a ZIP file by literally weighing the physical hard drive it's stored on.
That's a great way to put it. And when researchers realized parameter compression was fundamentally misaligned like that, they shifted to the other extreme, which is data compression.
Specifically, prequential coding.
Yeah. In this paradigm, you compress the model by sequentially compressing its training data. So the model predicts the next data point, and you encode the prediction error.
But if you do that, you're tying the code length directly to the dataset size. And if you're training on something massive like the pile or fine web, that length basically approaches infinity.
It does, and it gets worse. Prequential coding forces you to pay a bit penalty for the raw entropy of the data itself.
Oh, because of Shannon's source coding theorem.
Exactly. The code length is bounded by the entropy of the data distribution. So if your data set contains just irreducible, unpredictable noise, you are forced to spend bits encoding that noise.
Which makes no sense for ML.
Right. You're also paying for the model's full approximation error at every single optimization step, which assumes the model absorbs everything it sees, and we know that's false.
So parameter compression hits a wall because architectures are huge, and data compression hits a wall because data sets are huge and noisy.
Exactly.
So if both of these hit mathematical walls as we scale up LLMs, where does this third path come in? Because requential coding bypasses both by compressing the training trajectory.
Right, but the mechanics of how it transmits this trajectory are honestly wild. Let's look at the distillation setup.
Okay.
We have a student model, which we are trying to encode, and a teacher model that is already fully trained on the real data.
Now, normally, standard distillation would just have the student mimic the teacher on real data.
Right, but touching real data costs bits. So instead, the student proposes candidate batches drawn from its own current distribution.
Wait, how?
It generates these hallucinations using a pseudorandom number generator, a PRNG, which is initialized with a shared known seed.
Okay, so the student is just generating this massive set of potential updates based purely on its own internal state. And then the teacher evaluates them. But how does it communicate which candidate is the right one without transmitting a massive gradient vector back?
It uses something called relative entropy coding, or REC. The teacher looks at the pool of candidates generated by the student and selects the one that most closely aligns with the teacher's target distribution.
Right.
And crucially, the encoder only transmits the index of that accepted candidate.
Wait, so we are essentially just sending a seed and sequence of index numbers across the wire. We never transmit the teacher.
Exactly.
And the decoder just regenerates the accepted hallucinations of the student to train on. We are literally just sending an integer across the wire.
Yes, but the way that integer is encoded matters immensely. They use universal Elias delta integer codes.
Let's pause there because that is a bit heavy. For an ML engineer used to standard, 32-bit floating points, how does an Elias delta code actually function here, and why is it even necessary?
Well, when you're transmitting an index from a theoretically unbounded pool of candidates, you can't really use a fixed-width integer representation.
Right, because if you use 32 bits, you'd be wasting a massive amount of space if the index is usually just the number 3 or 4.
Exactly. So an Elias delta code is a universal code for positive integers that scales logarithmically. It works by first sending the length of the binary representation in a unary format and then followed by the actual binary value.
Meaning smaller numbers take significantly fewer bits to transmit than larger numbers.
Precisely. And this is where the synchronization cost is really determined. The probability of the teacher accepting the first few candidates is super high if the teacher and student are closely aligned.
Oh, I see. So if they are aligned, the accepted index is a small number, and the Elias delta code costs almost no bits.
You got it. The cost to transmit this index mathematically approximates the KL divergence between the teacher and the student.
Okay, that is brilliant. So the encoder and decoder start with identical initializations, identical update rules, and the same PRNG seed.
Right.
The encoder sends this highly compressed Elias delta index. The decoder gets it, uses its matched PRNG to regenerate the exact same pool of candidates, picks the one matching the index, and applies the update.
Yep.
We've completely synchronized a training step across two systems without ever touching real data or sending actual weights.
And because you only pay for the difference in knowledge, the KL divergence, the resulting code length completely divorces itself from both parameter count and raw data entropy. You're literally only paying for the exact amount of steering the teacher has to provide.
But, that creates a massive optimization problem, doesn't it?
How so?
Well, if our goal is to minimize the bit sense, we want the KL divergence to be basically 0. We want the teacher and student to always agree. But if the teacher just mimics the student to save bits, the student never actually learns the target distribution.
Yes. There is a severe tension there. The teacher has to run far enough ahead to pull the student toward the actual data set, but stay close enough that the KL divergence remains small.
Right.
To manage that trajectory, the authors introduced two specific optimizations for the teacher. The first is teacher smoothing.
Let me guess. This is about filtering out optimization noise. Because standard SGD or atom paths are incredibly jagged from microbatch noise.
Exactly.
If the student has to track every random walk the teacher takes in the loss landscape, we're wasting Elias delta bits on completely useless updates.
That is the exact rationale. So to fix this, instead of using the raw teacher checkpoints to guide the student, they use an exponential moving average, or EM, of the teacher's weights to generate the synthetic target data.
Okay, so by smoothing the trajectory, you get a stable gradient signal.
Right. The student no longer wastes bits trying to track high-frequency noise that doesn't actually contribute to generalization.
That perfectly handles the micro-level jitters. But they have a macro-level optimization too, right? ISO loss projection. This is where the geometry of the loss landscape comes in.
Yeah, ISO loss projection solves the problem of the teacher getting too far ahead. Periodically, the system actually resets the teacher's weights and optimizer states so they match the student perfectly.
Wait, they hit reset on the teacher.
Yep. The student is paused, and the teacher is trained briefly on real data until its predictive loss drops back down to where it was before the reset.
Oh, wow. Okay, think about the topology of a high-dimensional loss surface. You have this massive landscape with valleys of low loss. The teacher is down in a valley, the student is further up the hill.
Right.
The KL divergence between them is represented by the physical distance between those 2 points, which is getting super expensive to transmit.
So instead of trying to shout instructions up the hill, the teacher teleports back to the student's exact location.
This sounds like a scout running ahead on a hiking trail to find the destination. But instead of yelling directions back through the woods, which costs a lot of bits, the scout teleports back to the blindfolded hiker and just leads them by the hand down the absolute shortest path.
That's a perfect analogy because the teacher finds a completely new path down the hill, starting from the student until it hits the exact same elevation, the same loss level it was at before. It projects itself onto the student's iso-loss manifold.
And by doing that, the teacher maintains its predictive performance, but the KL divergence drops massively. They're physically closer in the parameter space now.
Exactly. The subsequent Elias delta codes required to pull the student down that new shorter path are exponentially smaller.
Okay, so if this mechanism solves the sync cost for a small model, what happens to our bit cost when we actually scale this up? Because as an ML engineer, you're beaten over the head with the intuition that parameter count dictates memory footprint.
Right.
But in their experiments, scaling from 1.7 million up to 1 billion parameters on Open Web Text, CFAR5M, and FineWeb, they found the exact opposite.
Yeah, this is the really mind-blowing part. When holding the loss fixed, meaning evaluating a small model and a massive model that achieved the exact same performance on a validation set, the billion-parameter models compressed to a significantly smaller bit size than the small models.
So you're telling me that adding parameters, literally making the raw file size bigger, results in a mathematically smaller compressed model?
Yes.
That breaks the brain of any conventional software engineer. How does having more parameters make you take up fewer bits?
Because Requential coding measures the efficiency of the training trajectory, not the architecture itself. Large language models are phenomenally sample efficient. They take larger, more accurate strides toward the target distribution.
So because a large model learns the underlying rules faster, it requires fewer corrections from the teacher.
Exactly. Fewer corrections mean fewer indices sent, which means a smaller total code length.
That means it's blowing past the theoretical floor of traditional methods. Like quantization bottoms out at 1 bit per parameter. You literally cannot compress a billion parameter model smaller than 1 billion bits if you're addressing the weights.
Right, but this method drops well below that floor. And this sample efficiency phenomenon extends to ensembles as well.
Wait, really?
Yeah, they tested an 8-model ensemble trained on FineWeb. Now, a standard engineer looks at an 8-model ensemble and sees 8 times the parameters, 8 times the storage cost.
Obviously.
But at a fixed loss, the ensemble compressed to a smaller bit size than a single model.
Is that driven by variance reduction?
Yes. The average prediction of an ensemble smooths out individual model biases, so it tracks the teacher's target distribution much more tightly.
And tighter tracking means a consistently lower KL divergence at every step.
Which shrinks the transmission costs so drastically that it entirely offsets the complexity of having 8 models in the first place.
Which brings us to the theoretical implications. Because this isn't just about saving SSD space on a server somewhere. The Requential code length actually slots directly into PAC-Bayes bounds. Let's break down what that means for generalization.
So PAC-Bayes bounds provide a mathematical guarantee on how well a model will perform on unseen test data. It bounds the test loss based on the training loss plus a complexity penalty.
But for modern LLMs, calculating a non-vacuous PAC-Bayes bound, meaning one that doesn't just say the error will be somewhere between 0 and infinity, is notoriously difficult.
Right, because the complexity term usually explodes as parameters increase. Traditional complexity measures look at the parameter count, or the L2 norm of the weights, which are just massive.
But because Requential coding minimizes a trajectory KL divergence instead, you can just swap it into the complexity term of the PAC-Bayes equation.
And when you do, it yields state-of-the-art generalization guarantees. Specifically for compute-optimal LLMs trained under the chinchilla scaling laws, where training tokens are roughly 20 times the parameter count. Yeah, it vastly outperforms previous bounds that relied on idealized zero-error 4-bit PTQ.
And the most crucial part of this finding is the scaling dynamic. The bound actually tightens as the model grows. The per-parameter complexity decays as a power law. For CIFAR, it decays at n to the negative 0.46. For FineWeb, it's n to the negative 0.15.
This power law decay is essentially the mathematical proof of why compute-optimal scaling works in practice.
I was just going to ask, does that mean if we scale up enough, The generalization gap essentially vanishes. Is this the proof?
It absolutely points to that. It certifies that scaling up doesn't just drive down empirical training loss, it inherently produces models that are increasingly compressible per parameter. The complexity penalty grows sublinearly.
So the difference between train and test loss naturally vanishes as we scale. It's incredible. And it also perfectly captures the mechanics of overfitting, which static parameter compression misses entirely.
Oh, completely. If you train a model for multiple epochs on the exact same data, traditional PTQ won't notice anything wrong. The weights just change values.
But the Requential generalization bound predicts a gradual divergence, right?
Yeah, because as the model transitions from learning general features to just memorizing specific training data points, the teacher has to issue highly specific, unnatural corrections to force the student to memorize that noise.
And that immediately drives up the KL divergence. The Elias delta indices get larger, the code length spikes, and the PAC-Bayes complexity penalty rises way faster than the training loss decreases.
Exactly. The trajectory itself reveals the memorization.
Which perfectly transitions into the final implication of this whole framework. By evaluating how a model absorbs data, we're actually evaluating the data set itself. And this solves a massive problem in information theory regarding something called epiplexity.
Epiplexity is such a profound concept. In standard information theory, we measure Shannon entropy, which is the total amount of raw information in a data set, including all the unpredictable noise.
Right.
Epiplexity, however, is the amount of information that is actually learnable by a model.
So if I have a data set of uniformly random strings, the Shannon entropy is massive. It's highly unpredictable. If you use prequential coding, which compresses the exact data sequence, the algorithm looks at the random strings and says, this is an incredibly complex data set. It'll take gigabytes to compress.
But an ML model looking at random strings learns absolutely nothing. The learnable structure is zero.
It's like separating the nutritional value of food from the cardboard packaging. Traditional compression was weighing the box and the food together, but requential coding just weighs the calories.
That's spot on. Because the student only encodes the updates from the teacher, and the teacher can't extract any generalizable rules from random noise, the teacher just stops giving the student meaningful updates.
The teacher essentially shrugs, the KL divergence drops to zero, and the code length stays tiny. The mathematical output perfectly matches the reality of the learning process. You've actually separated the signal from the noise.
They ran experiments comparing this across domains, actually. When evaluating random strings, requential coding found almost zero learnable structure, as you'd expect.
Right.
When evaluating CFAR5M images, it found substantial structure. But when evaluating text datasets like FineWeb, it found the highest density of structure.
Even though the raw pixel entropy of a high-resolution image is technically higher than a text file, the epiplexity, the density of learnable rules, is vastly higher in text.
Exactly. This mathematically validates why self-supervised text pre-training is the ultimate foundation for general AI. Human language is uniquely dense in learnable structure.
It's a complete paradigm shift. By encoding the training trajectory with self-generated data, we finally have an analytical tool that measures what a model actually learns, independent of its physical architecture and independent of dataset noise.
It's a massive step forward.
So to wrap this analysis up, we've gone from PTQ measuring the hard drive size to requential coding measuring the actual cognitive steps a model takes to understand a dataset. It proves large architectures are highly compressible, validates the chinchilla scaling laws through PAC-Bayes bounds, and quantifies the exact learnable value of our data.
It really covers it all.
But I want to leave you all with one final forward-looking thought. The math here proves that models are vastly more compressible than their parameter counts suggest. They operate effectively well below the 1 bit per parameter floor. Currently, we only discover this extreme compression retroactively by running distillation and calculating the KL divergence after the fact.
Right.
What happens if we can design a native training algorithm that inherently operates directly in this highly compressed mathematical space from step one? If the architecture itself lived natively in this sparse space, bypassing the need for a billion dense parameters entirely, could this be the key to training massive foundational models entirely on edge devices like smartphones?
That is the million-dollar question.
The theoretical space has now been proven to exist. The next era of ML engineering is figuring out how to build engines that start there. Thank you for joining us for this breakdown on AI paper slop, and we will catch you in the next analysis.